Welcome to the GeoMethod channel. Today we are solving another interesting geometry problem. Here is today's challenge. Can you find area of the triangle? Take a moment to study the figure. Then let us uncover the key geometric ideas that make the solution click. Here is triangle ABC with a right angle at vertex B. The horizontal leg segment AB has length 13, and every side is a whole number, and those two facts alone will fix the whole triangle. Focus on side AB, the one measured side of the triangle. Its length is 13 units, and every other length in the figure must be built from this single number. Because all three sides of triangle ABC are positive whole numbers, the triangle must be a Pythagorean triple. That one restriction is strong enough to pin down the other two sides exactly. Give names to what we do not yet know. Call the second leg segment BC, the letter B, and call the hypotenuse segment CA, the letter C, so we can write equations about them. The right angle at B lets us use the Pythagorean theorem. The two legs squared add up to the hypotenuse squared. So 13 squared plus B squared equals C squared. Replace 13 squared with its value 169. Turning that leg into a plane number is what will let us factor in a moment. Put that back into the relation to get 169 plus B squared equals C squared. Now the only numbers left are the two unknown squares and our constant. Move B squared to the other side, giving C squared minus B squared equals 169. Gathering the two squares together sets up a pattern we can break apart. Aha! Because the two unknown sides are whole numbers, the difference of squares turns the geometry into a short factor pair search. We can now use the factors of 169 instead of guessing side lengths. So, C minus B times C plus B equals 169. Two whole number factors multiply to 169, which we can now hunt down directly. 169 is 13 times 13, and 13 is prime. That means its only positive divisors are 1, 13, and 169, so there are very few ways to factor it. There are only two positive factor pairs, 1 times 169 and 13 times 13. We need to see which one can come from an actual triangle. If C minus B and C plus B were both 13, then B would have to be 0, and a side of length 0 is not a triangle. So we throw the equal pair away. Aha! The equal factor pair collapses the triangle, so the surviving pair gives C minus B equals 1 and C plus B equals 169. These two independent equations uniquely determine the two unknown sides. Add and subtract them next. Add the two equations together. The B terms cancel, and we are left with 2C equals 170, which isolates the hypotenuse. Divide by 2 to find C equals 85. The hypotenuse segment CA is 85 units long. Now, subtract the first equation from the second. This time, the C terms cancel, leaving 2B equals 168. Divide by 2 again to get B equals 84, so the missing leg segment BC is 84 units long. And 85 squared is exactly 7,225, the same number. The triple 13, 84, 85 checks out perfectly. Back on the figure, the two legs of triangle ABC are segment AB equal to 13 and segment BC equal to 84, meeting at the right angle B with hypotenuse segment CA of 85. These legs are all we need for the area. We now use the established triangle area theorem. Area equals 1/2 times a base times its perpendicular height. This is the axiomatic habit of mathematics. Euclid's elements organized results from stated foundations, a tradition that later shaped scientific thinkers, including Newton and Einstein. Here, the perpendicular base and height are 84 and 13, so substitute them directly. So the answer is 546. That completes the solution. A good geometry problem often has more than one beautiful solution. If you see a genuinely different construction, a high-level idea that leads to another solution, or a thoughtful adaptation of an existing method, share it in the comments. Even a rough idea is welcome. A sketch of the key move is enough. We greatly appreciate these contributions. With your permission, we may feature the approach in a future Viewer Solutions episode and acknowledge you by name or channel handle. Thanks for exploring geometry with GeoMethod.